Greetings, differential equation scholars, and welcome back to our next video in our series dealing with applications of higher order differential equations. We began chapter number 5 by taking a look at solutions to initial value problems. Most recently, we've started looking at the focus of section 5.2, which are boundary value problems. Sometimes we have conditions on the function, or maybe its first derivative, um, not just at one point in the domain, but at more than one point in the domain, perhaps at a left and a right endpoint of the domain. And one term, actually a pair of terms that come up in this context are eigenvalues and eigenfunctions. So we're going to introduce those terms here in the context of one of the problems from your textbook. We're going to be taking a look at exercise number 13 here from section 5.2. The problem that it poses in problem 13 is, suppose you have the differential equation y double prime plus lambda y equals 0, where lambda is some constant, and you impose a pair of boundary conditions. Here, the boundary conditions happen to be that the first derivative of the solution at 0 is equal to 0, and the first derivative of the function at pi is also equal to 0. So we have a pair of boundary conditions here, and we have a second order linear homogeneous differential equation with constant coefficients where there is a parameter lambda involved here. Now the question is, for which values of that parameter lambda do there even exist interesting solutions? There may be some values of lambda, some numbers, for which that differential equation has no interesting solutions at all. So in terms of vocabulary, we're going to introduce the following definition. We're going to say that for this problem, any values of the parameter lambda that produce non-trivial solutions, we're going to call those eigenvalues for this particular boundary value problem. So something is an eigenvalue for the boundary value problem if that value produces non-trivial solutions, solutions that aren't identically equal to 0. Those are what we're going to refer to as eigenvalues. Now, if they produce non-trivial solutions, there are solutions, solution functions, and those corresponding functions are called the eigenfunctions. So eigenfunctions is just a special way of saying interesting solutions to the problem. And the eigenvalues are the values of the parameter lambda that correspond to those interesting solutions. So let's take a look at this problem here in closer detail and find out what the eigenfunctions are and what the eigenvalues are that go with them for this particular boundary value problem. It turns out for these boundary conditions, these constraints on the first derivative, you can show, and we're not going to do it in this video here, but it's not too difficult an exercise to show that if lambda would be 0, so that we had y double prime equal to 0, or if lambda was some negative value, that we really don't have interesting solutions at all that correspond to those scenarios. But if lambda would be positively valued, there are in fact solutions. And we can find those solutions using the theory that we learned earlier in chapter number 4. So let's suppose that lambda is a positive number here. For right now, it could be anything. It could be 25. Lambda could be 3.9 for all we know. But for our purposes for solving the differential equation a little easier, let's suppose that that lambda value, that positive constant, is written as omega squared. If lambda is omega squared, then the differential equation is y double prime plus omega squared y equals 0. Now that's got an auxiliary equation of m squared plus omega squared equal to 0, so that m squared is negative of omega squared. And then our solutions for the auxiliary equation are m equal to plus or minus omega times I. They are imaginary solutions, complex solutions. And with roots like that, of plus omega I and minus omega I, then our fundamental set in this situation is going to be cosine of omega x and sine of omega x, so that we end up with a solution, a general solution to our homogeneous equation that looks like this: C1 cosine omega x plus C2 sine of omega x. That should be very familiar. That's kind of a canonical solution that we've learned about in chapter number 4 for that second order linear homogeneous differential equation. Okay, so now we know that the general solution would have to take that form. Let's apply our boundary conditions and see where that takes us. If this is the function, then its first derivative is negative C1 omega times the sine of omega x plus C2 times omega times the cosine of omega x. This would be our expression for our first derivative. And we had two conditions on that first derivative. The first one was that the first derivative at 0 has a value of 0. Let's see what that tells us. When I evaluate the first derivative at 0, one of our pieces is going to have the sine of 0. But the sine of 0 is equal to 0. So that piece will drop out of our equation entirely. The other piece will have the cosine of 0, which is equal to 1. So in the end, for solutions of the form that we have, the first derivative evaluated at 0 would have to be C2 times omega. But we were told, because of the boundary condition, that that this derivative at 0 was 0. So that means that C2 times omega has to be equal to 0. But omega can't be equal to 0 because that would have made lambda equal to 0, and we assumed that lambda was positive. So if omega can't be 0, that means now that C2 has to be 0. In other words, if C2 has to be 0 and our original solution looked like this, the expression that is currently highlighted, if C2 is 0, that means that that second piece of our general solution, the sine piece, drops out entirely. And we'll only have the cosine piece. The solution has to take the form y equal to some constant times the cosine of omega x. Aha. Well, we've applied one of our boundary conditions, but we had two. Recall that the second boundary condition was that the first derivative at pi was also equal to 0. So, since the first derivative is negative C1 omega times the sine of omega x, that means that if the first derivative evaluated at pi is equal to 0, then negative C1 omega sine of omega pi must be equal to 0. So we have another constraint that's come from assuming the other boundary condition that y prime at pi was equal to 0. Now, if we look at that equation there, We certainly don't want C1 to be 0. If C1 was equal to 0, we just have a trivial solution of y equal to 0. We can't have C1 equal to 0 and have something non-trivial for a solution. We also can't have omega equal to 0 because lambda is positive. So that means for this equation to be true, the sign of omega pi would have to be equal to 0. That's the only way to make that equation true. But when is the sine function equal to 0? Now, you know the answer to that from your fundamental trigonometry. The sine is equal to 0 whenever the input angle is some multiple of pi. Actually, in particular, some integer multiple of pi. So at angles like pi or 2 pi or 3 pi or 4 pi, anytime we are at the east or the west pole of the unit circle, we're going to have a value of sine that's equal to 0. And of course, that applies for negative integers as well, negative pi, negative 2 pi, and so on. And even at 0, the sign of 0 is 0. So what have we concluded then? Well, if the sign of omega pi has to be 0, then omega pi has to be equal to, we're going to say omega pi is equal to n pi, where n is got to be an integer value. It won't work for that multiple of pi to be anything other than an integer, because we don't have sine equal to 0 at 1/6 of pi or at 7/9 of pi. Only at perfect integer multiples of pi will we have what we need. So omega pi, that input angle, has to be equal to n times pi, where n is an integer. And that means that omega is equal to n. Omega must be an integer. Omega must be an integer. Well, now we have the solution to our problem. Omega is an integer n. Remember, back at the beginning, we said that lambda was omega squared. So if lambda is omega squared and omega is an integer n, then lambda is equal to n squared for any integer value that we might have. Those are what we call the eigenvalues. Remember, the eigenvalues were the values of lambda at the beginning of the problem that produced interesting solutions. We now know what those are. They are squares of integers. So things like 0 and 1 and 4 and 9 and 16. Those squares of integers are going to be our, what we call the eigenvalues for this problem. And corresponding each one of the possible integers will give us an eigenfunction. So we said earlier, we knew that the solutions had to be of the form cosine of omega x, but we've just found out that omega has to be an integer. So that means that our eigenfunctions are going to take this form. We might call them y sub n equals cosine of nx, where n, again, must be integer valued. For integers n, the cosine of nx will be a solution that we refer to as an eigenfunction. Here at the end, I've tabulated a few. There's going to be infinitely many eigenvalues and eigenfunctions, but this is a table of some of them for some integer values. So if n is 0, then lambda, which is n squared, is 0. And the eigenfunction for that would be the cosine of 0x, which is just the cosine of 0 or 1. So we see that we actually do have constants as solutions when lambda is equal to 0. What if n is 1, 2, or 3? Well, for those integer values, the eigenvalues, remember, are the square of omega, which is the square of n here. So our eigenvalues for n equal to 1, 2, and 3 would be 1, 4, and 9. would be the eigenvalues. And those correspond to eigenfunctions of the cosine of x, the cosine of 2x, the cosine of 3x. Those are the eigenfunctions that correspond to the given eigenvalues. Notice here that the omega here is the square root of the omega squared that we have there. Now, there also could be negative values of n. They would produce eigenvalues that would be positively valued, but they would produce eigenfunctions where we would have a negative integer multiple of x as well. So if n is -1, we have an eigenvalue of 1 and an eigenfunction of the cosine of -x. So those are some of the possible eigenfunctions. There's infinitely many of them. Just keep adding, making your integers larger and larger or smaller and smaller, and we've got an infinite set of eigenfunctions and corresponding eigenvalues. And that's another type of problem which is introduced in section 5.2. Some new vocabulary, the vocabulary of eigenvalue and eigenfunction. And what we want to remember about those terms is that for a given boundary value problem, if that boundary value problem involves a parameter, like lambda here, that boundary value problem may only have interesting solutions for certain values of lambda. And the values of lambda that produce interesting solutions, non-trivial, non-zero solutions, those values of lambda are known as eigenvalues, and the corresponding functions that they produce, those non-trivial solutions, are known as the eigenfunctions. Eigenfunctions are solutions to boundary value problems, and eigenvalues are the values of the parameter that beget or produce those solutions. Very good then. I hope you have enjoyed this video and found it to be informative. We will see you again next time on a YouTube channel near you.